Thank you very much, Andy, for such a nice introduction. I'm afraid that the packaging will be better than the meat, but it's very nice. And I also, by the way, always warn audiences not to applaud beforehand because you will always have regret later. It's nice to be back at Foothill College. Actually, when I first came to this part of California more than 20 years ago now, I had a lot of free time, which is not the case now, but I had quite a bit of free time in the evenings, and I came up here and took some courses in creative writing, actually. It was somewhat by accident. I just wandered into the wrong room by mistake. And I have the fondest memories. I think that Foothill College, to the extent that I can write, taught me how to write. So it's very nice to be back here and to be back part of the lecture series. It's been a while since I've given a talk here. My last talk was what happens if we find ET, and in that I described a little bit about how SETI, and in particular the SETI Institute, which, by the way, I don't know if Andy mentioned, is in Mountain View, so a local institution here, how we're doing the experiment. Tonight I'm going to simply try and provoke you. This is not entirely malevolence, but it's just to suggest other ways of doing SETI that you might think about. And if the hit rate on these ideas is as much as 5 or 10%, that'll be pretty good as far as I'm concerned. So, first off, here's just a picture of the universe, or part of it. You see a whole bunch of stars. There's some, hot gas and so forth there, some cold gas you can't see. In the background, some galaxies. The number of stars in our galaxy is on the order of a couple of 100 billion. I think most of you know that number. The question that has been asked now for a very long time, and that we're finally getting an answer to, is, well, how many of them have planets? Now, those of you who follow this thing know that we've discovered more than 400 planets around other stars. That, per se, is not so interesting. What's really interesting is what fraction of stars have planets. And if you talk to Jeff Marcy, who's spoken in this series, or other people who look for extrasolar planets and say, well, Jeff, if you had perfect instruments, what fraction of stars do you think would show planets? And he says, well, maybe half, maybe 3/4. Okay? Now, for an astronomer, half is the same as all. Okay? You don't worry about factors of 2. In astronomy, pi is 1 or something like that. So what that means is that there are on the order of 1 trillion planets in our Milky Way. And if none of those seem suitable enough for you, if you're particularly picky about your planet, you can always go to another galaxy and find another 1 trillion planets. But this is a big number. I just want to emphasize this. People say, why do you think there's life out there? There was a reporter at the Institute recently who asked me, do you really think they're out there? Which I found a very bizarre question to ask of someone who's working at the SETI Institute. I mean, why would you do it? But I said, yes. And he said, well, why? And I said, well, it really comes down to this. It just comes down to this number, because if only 1 in a million of those planets meets the requirements for your gusto-grabbing, free-living lifestyle, that's still 1 million worlds just in our galaxy. So, the numbers look good because they're large. There's something else. There are other indications that might suggest to you that maybe what's happened on this planet is not really a miracle, and that is the fact that life got started here very early. This is a photo I made down in the northwest corner of Australia, in the Pilbara Hills. You see these sort of round things. This laser pointer isn't really a laser pointer. I'll telepathically tell you where to look. And there's a business card there for size, or something like a business card. You see those round things that look like frozen cantaloupes. Those are fossilized stromatolites. Okay, those are just the colonies of bacteria. And we know how old this rock is from radioactive dating. We know that fairly accurately. It's about 3.4 billion years old. What this is saying is that 3.4 billion years ago, right, there was plenty of life on Earth. So, since the Earth is only 4.5 billion years old, what this is saying is that life got started very quickly on Earth. And that suggests, doesn't prove, it's only an example of one, but it does suggest that life wasn't a very difficult experiment. Certainly not an improbable experiment, because it got started very quickly. Okay, so how are we looking for not just life, but the kind of life that could hold up its side of the conversation, namely intelligent life? Well, I think many of you heard Jill Tarter speak here recently talking about the Allen Telescope Array, which is a joint project of the SETI Institute and the University of California at Berkeley, to build our own telescope to do this sort of search. And for the Berkeley people, also to do some top-notch radio astronomy. By the way, there's a dime in this photo for scale, but if you don't see it, you can see me going around flashing the antennas. This thing is located about 300 miles from where you're sitting, up in the Cascade Mountains of northeastern California. And it's located there, by the way, not because of the cuisine, but because it's surrounded by mountains and therefore shielded from all the interference from the Bay Area. In any case, it's named after Paul Allen, who's given the money to get this thing underway. And it's, as I say, an instrument that's really designed from the get-go to be very good for SETI research. This is a big step forward, by the way, because people will often say, SETI is celebrating its 50th year this year, in fact, in April. You haven't found anything? Doesn't that embarrass you? Or, don't you get discouraged or something like that? Keep in mind, we've had to do these experiments intermittently using other people's antennas. So, it's like trying to find the cure for cancer, but always having to borrow the microscope. It's very slow going. This will have an in-house telescope. We can use it 24/7. That's a factor of 10 improvement in speed right there. Covers a very much wider range of frequencies. These are all technical things. There will be a few technical things in this talk, not too many. I'm told that every time you show a graph, this was a lesson I learned in grad school, every time you show a plot, you lose 10% of the audience. So I have 12 plots in this talk. Put them all at the beginning so that you don't have to suffer long. And it can also, this is a really important point, and this has to do with the nature of antenna arrays. It can look at more than one star at a time, so you're not just looking at one star and then looking at another star and looking at another star. When I say looking at a star, of course, I mean we assume that they have planets around them. This is an aerial shot I made about a year ago. There are currently 42 antennas in this array, but the design goal is to make 350 of them. But it's not the only way we do SETI. We also do optical SETI, so-called optical SETI, and this is a photo up at the Lick Observatory. This is a telescope that's about 1 meter in diameter, so it's, a small telescope, an old telescope, but perfectly adequate for aiming at nearby stars, using some electronics in this white box behind. That, by the way, was put together by Shelley Wright here, who was a student at the time, an undergraduate student at UC Santa Cruz, and look for very brief flashes of light. Right? If you get a brief flash of light in a nanosecond, in a billionth of a second, and maybe you count, 100 photons or 1,000 photons, that's got to be something special, because the stars don't do that. Right? A star 100 light years away, like the sun, would produce less than 1 photon in a nanosecond for a 1 meter telescope. So this is another way to look for life in space. They may be flashing us with their lasers. We have these dual approaches. Now, this whole field was begun, as I mentioned, 50 years ago by Frank Drake. Here's Frank. He always put on a tie and a jacket when he's standing out in the cold there in West Virginia. This is the 85-foot antenna that he used in the spring of 1960, pointing it at 2 nearby stars, hoping to eavesdrop on signals coming from those stars. This was Project Ozma. And he started what is known as today's targeted search strategy, because he didn't point the antenna at random. He picked 2 nearby stars. They were about 11 or 12 light years away. They were stars like the sun, and he looked at first one and then the other. He actually scored on the second one. He got a signal, but it turned out to be the U.S. Air Force, so that didn't count as alien intelligence. There you go. Okay, now, I want to emphasize, this was the strategy that was chosen then, and this is the strategy we still use a lot today. The SETI Institute is very keen on targeted searches, and the Allen Telescope Array is planned to also look at individual stars, okay? And the idea is that you look at the nearest ones first and you work your way out. But I'm going to suggest tonight some alternatives to that. Now, this plot, which was made up for a magazine article, just gives you some idea of how much search space we've looked at, right? I mean, you're looking for ET. You haven't found it. Well, this tells you why. These are all the, just a couple of the parameters of the signal, right? They've just been plotted as 3 axes here. And you can see various experiments. Actually, this Allen Telescope Array is, for the future. We haven't actually filled that in yet. So you can see that very little of the search space has actually been examined.